Okay, welcome everyone to this last episode of this second season of MIDI, the MIDI Infrared Discussion webinar series. I'm Simone Deliberato, and together with Vincenzo Giannini, I will be your host today. Today, we are honored to have with us Professor Paolo Biagioni from Politecnico di Milano. Paolo will introduce us to plasmonics in doped semiconductors, which is possibly the only major platform of mid-infrared nanophotonics, which we didn't cover yet here on MIDI. Some practical information. The talk will last roughly 45 minutes, following time for questions. And please note, this webinar will be recorded and it will be released on our YouTube channel together with all the other episodes of this season in the next very few days. I will send an email to everyone when the episodes are uploaded. Okay, that's all. So please, Paolo.
Thank you, Simone, and thank you, Vincenzo. Very, very glad to be here and to fill this last gap in your topics. So let me share my screen. You should see the presentation. Yeah, okay, great. So as Simone said, I'm going to discuss plasmonics in the mid-infrared using heavily doped semiconductors. And I was asked to mix the report of our results with an introductory and broad overview on the topic, which I'm very, very happy to give. And I didn't keep the two parts separate, so rather I will discuss the results by opening some windows that will give you all the introductory concepts slide by slide for the various topics that we will discuss. And so just let me give you a brief outline of what you will hear during this talk. First of all, I will try to motivate why we should be interested in semiconductor mid-infrared plasmonics, why it's possible, first of all, and why it's interesting. And I will then cover the main aspects that I believe should be discussed in this framework. First of all, some material science, so to say, because heavy doping of semiconductors to reach plasmonic behavior in the mid-infrared is challenging, and so specific strategies need to be put into work to achieve this. And I will do this focusing especially on germanium, because as I will tell you in a second, this is the platform which we considered for our activities. So then I will show you nanoantennas made of germanium and some applications in the field of sensing, which is one of the main application fields for mid-infrared plasmonics. I will then try to address one hot question, I would say, which is how do semiconductors compare with metals for mid-infrared plasmonics? And we will see that it's not an easy question to answer. And then I will cover other applications, or again using nanoantennas as a benchmark, and I will discuss ultra-fast and nonlinear approaches with the mid-infrared plasmonics. So first of all, a brief introduction saying why mid-infrared plasmonics and why doing this with semiconductors. So without going into semiconductors yet, just why mid-infrared plasmonics, I think that this community does not need to hear this. Mid-infrared is a crucial and strategic window, especially for vibrational sensing and to identify the fingerprint of specific classes of molecules for health, security, analysis, and so on. But of course, there are all the application fields of plasmonics that we are used to in the visible that are also translated to the mid-infrared. So the enhancement of infrared vision systems or light detection in general, possibly also some applications in terms of enhancing the infrared response of solar cells. And more generally, plasmonics is about enhancing light-matter interactions between nano objects and wavelengths which are much larger than the objects that you consider. And this was the, let's say, starting point for mid-infrared plasmonics, which on the one side dates back several decades, but has become a very well-focused field of research only over the last 10 or 15 years, I would say. So here are just 3 examples which are used not as a comprehensive overview of what is being doing, but just as an excuse to tell you a few things about infrared plasmonics. So here you have one of the seminal works, one of the very first works with gold antennas used to detect molecules. So you have a layer of molecules which gives basically no fingerprint signal when it's placed on a substrate, while if you place it on top of an antenna, you see the broad antenna resonance, and on top of it, the markers of your molecules appear thanks to the enhanced interaction with the infrared light. And then this opened a whole field which is typically known as SEIRA, surface enhanced infrared absorption. And so people started discussing new geometries in order to make these sensing platforms more efficient. And so people started, for example, exploiting extreme field enhancements due to lightning rod effects at the apex of specific nanostructures, or considering more complex structures in which interferential line shapes appear, and therefore narrower peaks improve the sensitivity to the sensing of the sensing platform. All these examples that I'm giving here, and many, many more that one can find in the literature, are made with gold antennas. So this was the starting point of mid-infrared plasmonics, because gold was the material of choice also for visible and near-infrared plasmonics. So why moving to semiconductors? First of all, why can we move to semiconductors? That's because the plasma frequency of these materials, which is the frequency that marks the onset of metallic behavior, scales as the square root of the carrier density. This means that by proper doping the semiconductor, one can bring this plasma frequency in the mid-infrared and make the semiconductor behave as a metal or as a plasmonic material, as we will argue, also for these frequencies. The higher the doping, the higher is the window, the spectral window for the exploitation of plasmonic behaviors. And so more recently, people started exploiting semiconductors for several reasons. One is that this formula already tells you that there is an intrinsic tunability of the behavior. So we can control the spectral response by playing with the doping, and this we will see during the seminar. And then semiconductors, of course, come from decades of development in the microelectronic industry, and this means that we have high quality already available, both in terms of material quality and in terms of processing in the foundries. And finally, this is a more subtle point, semiconductors allow for what we could call a truly plasmonic behavior in the mid-infrared, because metal in the mid-infrared, the noble metals in the mid-infrared behave more or less as perfect conductors, which means that the real part of their permittivity, the negative real part of the permittivity, is very, very large. And so it does not compare well with the positive dielectric permittivity of the dielectric surrounding that surrounds the nanostructures. And this is detrimental when metamaterials needs to be developed. So we want a system which has a small real part of the refractive index, of the electric constant, in order to develop properly the concept of metamaterials. And also, as we will see, all these materials allow for a direct access of the epsilon near zero phenomena, which require a vanishing dielectric constant, which is of course not the case for perfect conductors in the mid-infrared. And so we started seeing in the literature examples of semiconducting antennas made both from group 4 and from 3-5 alloys, and fabricated with different techniques, as much as we have for metals, basically. And this concept that I'm describing here is valid for all semiconductors, but as I said, we focused mainly on germanium nanoantennas, and the framework for this research was a European project, Gemini, which stands for Germanium Mid-Infrared Plasmonics for Sensing, which was financed by the European Community. And the reason why we chose germanium is quite clear to us, at least. First of all, we wanted to develop a group 4 platform, because group 4 materials can be processed without any problem in silicon foundries, which is, of course, the starting point for mass production from the point of view of industry. And among the group 4 materials, we don't choose silicon, but rather germanium, because germanium has a lower effective mass. It's lower by roughly a factor of 2, which means that for the same doping level, we achieve a higher plasma frequency. And finally, germanium has no optical phonons in the mid-infrared spectral region. So it's a very transparent material when it's not doped, which is not the case for silicon, because there is an optical phonon which is made partly active in the infrared when defectivity is taken into account, and which typically limits the transparency window of silicon around 9 micrometer wavelengths. So for longer wavelengths, silicon starts to be a problematic material. So within the consortium, we studied materials. The platform is germanium grown epitaxially on silicon. We fabricated and exploited antennas, and we also focused on dielectric waveguides for the on-chip distribution of the signals, and on some concepts based on bolometer detectors. But what I'm going to discuss today is mainly material science and plasmonic antennas. And now it's time for the acknowledgements. First of all, because I don't want to have them in the end when we have no time. And second, because the work that I'm going to present is not the work done in my university and my laboratories, but it's the effort of a large consortium. And I'm only just lucky that I was able to coordinate these efforts. So I hope I will also be a reasonable presenter of them. So we had the unit in Milano, which took care of material growth and all the plasmonic design and simulations. The group at the Sapienza University of Rome for the infrared spectroscopy and sensing. The University of Glasgow with the nanofabrication facility for all the fabrication efforts. And the group at the University of Constance for ultra-fast infrared spectroscopy. And this was the consortium. And then I would like to acknowledge also the University of Padua for the secondary ion mass spectroscopy that you will see during the presentation. University of Pisa for the simulation of quantum scattering processes in the material. And finally, an acknowledgement to Thierry Tagliarchot, who very kindly invited me to join him and write together a review on the topic, which was published last year and was for me a very nice occasion to rethink all the concepts that I'm going to discuss. So we start with material growth. And the typical semiconductor growth is made by CVD, chemical vapor deposition, meaning that you have precursor gases, and this is a reactive deposition process which is favored by the heating of the sample substrate, so that there is a dissociation and deposition on the sample. This variant of CVD, which is called the low energy plasma enhanced CVD, also exploits a plasma source, which exploits an argon jet. And this plasma is another degree of freedom, which basically allows to independently control the plasma the diffusion of the atoms on the sample, which is controlled by the sample heating mainly, and the kinetics of the growth, which is influenced strongly by the plasma. And by doing so, we are able to grow high quality materials, but with fast growth rates. And this is especially crucial for plasmonics in the mid-infrared because the thickness of the layers that you need to grow is considerable, is hundreds of nanometers or even micrometer. So you need a fast growth process. And the quality, as I said, is a single crystalline quality because the plasma is a low energy plasma, so it does not destroy the quality. And we have gases to grow silicon, germanium, and then to dope the materials negatively with phosphorus or positively with boron. So the typical material characterization that we perform on our films after growing a germanium film on silicon is taking a Fourier transform infrared spectrum. We collect the reflectivity of the sample, and the typical reflection spectrum that you get from a heavily doped semiconductor film looks like this. So for low frequencies, you are below the plasma frequency, and this means that you behave as a perfect mirror, more or less, and indeed you have unitary reflectivity. Then you have a sudden drop, and this is related to the plasma frequency. This is the onset of the metallic behavior. And so you have a dramatic change in the dielectric constant, which the real part goes from negative to positive. The metal becomes a dielectric material, if you want. And in this change of the dielectric constant, you reach a point where there is a minimum, because basically you become index matched to the surrounding, so you have very high transmissivity. And then at even higher frequencies, you have oscillations, which are Fabry-Perot etaloning inside the film, which is typically in our situation is a 1 micrometer thick film. And here you have a dielectric material acting as a poor cavity, basically. And this is indeed what we see when we characterize several films. All of these spectra are taken for films which possess different doping levels, and you can see the oscillations at high frequencies and the edge due to the plasma behavior. And you can also see that this edge translates towards higher frequencies as the doping is increased, as expected for the basic formula. So in order to extract the dielectric constant from these spectra, we need to model them. Typical approach is to consider a Drude-Lorentz model, where you have the Drude term that describes the behavior of the free electron against the positive background of the ion cores. Then you have a set of oscillators which can describe discrete excitation energies, and these can be associated either with interband transitions in the material or with phonon excitations. And finally, since you don't consider typically all the excitations inside this term, you still have the tail of all the excitations that are far away from your spectral window, and all these tail contribute a positive background in the permittivity, which is this epsilon infinity. And the numerator here in the Drude term is what we call the plasma frequency. And as you see, this scales as expected as the square root of n over the effective mass. Now, if you choose your semiconductor material properly, you can imagine that you are far away from absorption transitions, because otherwise you would have a poor material in terms of the losses. So let's imagine that this term does not play a significant role. So we can imagine that we use this formula, which is indeed used very often in the literature to fit spectroscopic data from semiconductor films. And here you can see that the zero crossing of the real part of the dielectric constant occurs for a specific frequency, which is actually different from the plasma frequency, mainly because it takes into account the screening of this epsilon infinity polarizability. and also because there is a scattering rate that comes into account and which slightly changes the zero crossing. So this is an important concept, and one typically would like to take the spectra, fit them with this model, both to have an experimental characterization of the dielectric constant and also to derive the doping level of their own material. And indeed, if you do the fitting of this formula and you use it to extract the doping level, you can see in this graph, in one axis, you have the doping level extracted from Fourier transform spectroscopy. On the other axis, you have the doping level extracted from whole bar electric measurements. And you can see that the two agree with each other very, very well. So a little bit more insight into this formula, just to make everyone aware that this formula contains a strong assumption, which is that the scattering rate gamma that appears here in the denominator of the Drude term is a constant. So this assumes that the scattering rate is frequency independent. And this is not true for the scattering mechanisms that we encounter for these materials in the mid-infrared range. So one can take another approach, which is model independent by exploiting Kramers-Kronig relations. So directly playing with the reflectivity data and extract without any a priori assumption on the model, the dielectric constant. In order to do so, we have to prolong our data from 0 to infinity in order to perform the proper integrations. I don't want to spend time on this, but the important point is that then you have a model from which you can somehow extract a frequency-dependent scattering rate. So you can imagine that you still have this formula, but now gamma is a function of omega, and once you have extracted epsilon from your Kramers-Kronig analysis, you can compute this frequency-dependent scattering rate. And when you do so, you exactly see that the scattering rate is nothing but constant over the mid-infrared spectral region. And indeed, you can see that these are two measurements performed at room temperature or cryogenic temperatures, and you can see that the scattering rate increases with the frequency and decreases with temperature, and this is due to the freezing of the phonon excitations. And indeed, one can take a single electron perturbation model, considering the electrons in the conduction band, which lay in the L valley of the germanium material, and calculating from first order perturbation the scattering rate due to charged impurities, which means the ionized dopants, and the optical phonons. And one qualitatively, at least, retrieves the same behavior encountered experimentally. So these must be taken into account if the modeling that one is performing and the simulations that one is performing are sensitive to this frequency dependence of the scattering rate. And this is a more accurate modeling, I would say, for the whole losses description. Now, as I said, there are many technological issues to face when you want to dope heavily your semiconductors. And in order to access the whole mid-infrared region, one typically targets doping levels in the 10 to the 20 range per centimeter cube. And here you can see an interesting thing. So this is an experiment in which we grow the material with a flux of phosphine in order to get a negative doping. And you can see that as we increase the flux of the phosphorus precursor in the chamber, we increase the carrier concentration, which is measured in this case by whole bar measurements, but could also be measured by infrared spectroscopy. And at a certain point, we reach a saturation. The saturation is expected because there is a solubility limit for dopants inside the crystal network. But the interesting thing is that if we perform secondary ion mass spectroscopy, and instead of counting the free carriers, we count the number of doping atoms that are incorporated, we can see that still we have a saturating behavior, but the concentration of doping or dopants is 3 times roughly the concentration of electrons. This means that there is a whole range of inactivated dopants. So the atoms are there, but they did not give their electron away. And this is typically due to the inability to ionize the dopant, which can happen, for example, because they don't place themselves in a substitutional site, but rather in an interstitial site, or because they create complexes with other defects, such as vacancies, or because they cluster with each other, which is a typical occurrence, for example, nearby dislocations. So one has to make these inactivated dopants active. And in order to do this, basically, we employ annealing strategies typically in order to provide thermal energy and allow them to adjust themselves in the proper substitutional positions. And one can go for rapid thermal annealing on the millisecond time scale, flash lamp annealing on the microsecond time scale, or laser annealing on the nanosecond time scale. And laser annealing turned out to be very effective because it's basically a sudden melting by means of a UV laser with nanosecond pulses, and then an out of equilibrium recrystallization, which typically creates a very favorable environment for the activation of the dopants. And indeed, you can see this is the result of applying laser annealing. First of all, we draw a sample with a very high concentration of dopants. This is the highest we could get. This is a profile of the dopant concentration along the thickness of the film. So it's a 500 nanometer thick germanium film with an incorporation which is almost 10 to the 20. And then we measure it as grown, which is the blue spectrum, which shows no clear signature of a plasmonic behavior in the mid-infrared. And after the laser annealing, which is the black spectrum, in which you can see that a clear plasmonic behavior due to the activation of the dopants is visible. And you can see we have a relatively high plasma frequency, which is more than 2500 wave numbers. And actually our best results so far is this one with a plasma frequency of about 3500 centimeter inverse centimeter, which means that we have a doping density which is more or less equal to the incorporated doping, and which means that we cover the whole mid-infrared down to 3 micrometer wavelengths, basically, with these materials. So these are the materials we play with, and now I will show you a few applications of this in terms of antennas. First of all, these are germanium antennas grown on the silicon substrate with the heavy doping of the germanium. This is a material which still has a relatively low plasma frequency, around 10 micrometer wavelengths. And the antennas are fabricated with electron beam lithography and reactive ion etching techniques. And then we do the typical characterization of the antennas. First of all, we measure extinction spectra. So this is the experimental extinction spectrum from these antennas. And you can see that there are 2 peaks which can be related to plasmonic resonances. And indeed, these peaks disappear when we measure the same material without doping, which is the dashed line. The same antennas without doping, which is the control dashed line. And then one can use the electric permittivity extracted from the fitting that I described before and can run simulations. And you can see that there is a fair reproducibility of the experimental data. And with the simulations, we can also give a meaning to these 2 resonances. So the low energy resonance is associated to plasma oscillations, which occur mainly at the interface between the germanium and the silicon substrate, while the high frequency one is associated to plasma oscillations, which are mainly associated with the air interface. And this is very peculiar to these antennas and to most of the semiconductor antennas, because one feature of these systems is that they are typically grown epitaxially on high index substrates. So it's a situation which is different from the typical plasmonic system in the visible, which is grown on a glass, so on low index materials. Here, the material of the substrate has a high index, so there is a very strong contrast of indexes between the air and the substrate, and this tends to split the two modes at the two interfaces. And the most interesting mode is the high frequency one for two reasons. One is that, as I said, achieving high plasma frequencies is challenging. Therefore, we want to have a mode which is as high as possible in energy for a given plasma frequency. And the second point is that these fields are mainly located in air, while these fields are located towards the substrate. And of course, if you want to interact with something else, typically with molecules, this configuration is favorable. And what we did was a proof of concept. We deposited 40 nanometer conformal layers of PDMS on top of the antennas in order to perform a controlled experiment, which mimics a sensing experiment. And you can see the results. These are three different geometries: a single antenna, another single antenna but with different length, and a double wire antenna with a gap in the middle. And the dashed spectra are those of the clean antennas. Then we put the PDMS on top and we measure the solid lines. And what you can see is that you have this vibrational fingerprint around 800 wave numbers that is associated with the PDMS response, which clearly appears on top of the antenna spectrum. And you can also appreciate that the strongest signal comes from the gap antennas, because the gap favors the localization and the enhancement of the fields. So in order to understand these signals and also to evaluate the associated enhancement, we run simulations. And you can see that if we place the PDMS in the simulations, we reproduce the spectra. The blue are the spectra for the light polarization along the antenna axis. So you have the resonance of the antenna, which is actively exploited, while the red spectra are those for perpendicular polarization. And I need to stress two things here. One is that you can see something also in the perpendicular polarization, so when the antenna is not involved with the resonance. And the second one is that this feature here has a typically up and down behavior. So with the simulations, we can give a reason for these findings, because we can play with the simulations and we can place the PDMS only in the hotspots of the antenna or only everywhere else, but not in the hotspots. And basically, the PDMS everywhere else has a volume which is roughly 100 times the one of the PDMS in the hotspots. So now we can see the two spectra separately. And these are the results. For the perpendicular polarization, you can see that the whole signal is in the red line, which is the signal coming from the extended PDMS layer. But if you consider only the material in the antenna gap or in the antenna hotspots, no signal comes from it because no resonance is involved in this situation. While in the parallel polarization, you see the signal both from everywhere else, as much as in the perpendicular polarization, but also from the antenna hotspots. This gives you a clear evidence of the enhancement provided by the antenna. And indeed, this up and down feature here that we reproduce in the spectra comes from the interplay between these two features, is reproduced only if those two features are both present. And from the simulations, we can also estimate an enhancement factor, which in this case is of the order of 200. So it's not so large compared to some record values with gold, but I would say that this was not the best material available yet, because this was done previous to some other efforts in material development. And also that with semiconductors, you can anyway accept a trade-off between technology, quality, and mass production opportunities on the one side, and performance on the other side. And you might be wishing to trade a bit of one for the other one. And so one has to weigh pros and cons as usual. And we also did an experiment with liquid sensing. I'm not going into the details, but again, we could see that with this simulant of explosive liquids, we could appreciate the enhancement due to the plasmonic antennas. And now the comparison between gold and germanium, which is a prototypical comparison between metals and semiconductors in the mid-infrared. And I will do this by comparing two figures of merit. One figure of merit for the propagation of plasmons, which is then associated with losses, basically, and one figure of merit for the confinement of the fields at the surface of the plasmonic material. And here you can see that this is gold in the mid-infrared, with very low losses, but also with very poor confinement. And this is germanium in the mid-infrared, with lower losses, higher losses, but also better confinement properties in terms of material-related confinement, because of course then you can also confine the field by using geometries. But this is the confinement which is granted by the material itself. And you can see that the germanium in the mid-infrared is very close to this line, which is gold in the visible, because the line covers the whole spectrum. So germanium in the mid-infrared is a plasmonic material, which we are used to, as much as gold is a plasmonic material in the visible and the near infrared, while gold in the mid and far infrared is a perfect metal, which has different features from what we could call a plasmonic material. And this chart gives you a rationale for the difference. And indeed, it can be demonstrated, and it's discussed in many papers, that losses are a required ingredient in order to make field confinement possible. And therefore, I make a long story short, because I'm slightly late in my schedule. We made a comparison between the performance of germanium and gold plasmonic structures, and what you end up with by running simulations is that the enhancement that they provide is roughly similar. By optimizing the gold structures, we obtained 4,000 of enhancement, and by optimizing the germanium structure is 1,000. So the order of magnitude is still the same, and the comparison is not so unfair to germanium eventually. And the germanium can also take advantage of fabrication possibilities that are not available with noble metals. For example, here you can see a freestanding membrane of germanium slits. And here the membrane is broken in order to really demonstrate the structure. And this is something, for example, that is very good from a plasmonic point of view, because you get rid of the substrate, which is often detrimental, and is not really possible with a metal layer. So you have to take into account technological perspectives also when you weight semiconductors against metals. And now I will end up with the last 7 minutes with some applications in the ultra-fast and nonlinear regime. Because so far we have seen doping by static action on the semiconductor. We control the doping during the growth. Once it's set, we cannot change it anymore. But doping can be also changed dynamically, either by electrical injection of carriers, which is very often used in the terahertz regime, but it's not feasible in the mid-infrared because you would need too many carriers, or by optical means, which is instead available as a path in the mid-infrared. So what we did was to inject carriers in the conduction band of germanium with a near-infrared pulse, which excites carriers at the gamma point, and then the carriers scatter very quickly in the L valley, which is the conduction band minimum, and this creates a transient population of carriers in the material. And this population is also further boosted by 2-photon absorption of the same laser in the L point of the Brillouin zone. And so we have this pump pulse which excites the carriers, and then with the same source, we also create mid-infrared pulses with a parametric amplifier. And here you can see that the dashed spectrum is the transmission spectrum of the mid-infrared pulse when no pumping occurs, while the red one is the transmission spectrum after pumping. And what we are pumping here is an array of undoped germanium antennas. So these antennas would not be plasmonic, but they are transiently doped by the pump pulse. And then we can study the transient plasmonic behavior with the probe pulse in the mid-infrared. And what we get is this graph in which you have frequencies in the vertical axis and the time in the horizontal axis. So we measure the spectrum as a function of the time delay, and you can see a feature which red shifts with time. And this is exactly the same plasmonic resonance that we saw before, which is transiently excited by the electron population. And then as time goes by, electrons go back to the valence band, the doping is reduced over time, and thus the plasmonic behavior red shifts over time as well. And this is exactly what we are observing here. And we were also able to simulate this behavior by simulating the spectra of the antenna as a function of the doping density. So the doping density simulates the time that goes on. And you can see that this portion here corresponds very nicely to our experimental results. And one thing that I would like to stress is that in order for these simulations to work, we had to take into account that when we excite a carrier, we don't just create an electron population, we also leave holes in the valence band. So we effectively have two plasmas, one of electrons and one of holes, and they both oscillate. And the whole plasma, they are very different from electron plasma because in the valence band, you have the transition between the split of holes and the light and the heavy holes, which is an absorption transition exactly in the mid-infrared, exactly in the energies that we target. Indeed, here you can see the spectrum of N-type germanium with the clear plasmonic behavior, and the spectrum of the P-type germanium, which does not have a very marked plasmonic edge because losses kick in due to interband transitions in the valence band. So holes are a very bad plasma in germanium for plasmonics, but they are naturally excited here, and therefore we have to take both plasma into account in order to reproduce our results, and especially to take properly the losses into account. And with the pulsed mid-infrared lasers, we can also work on nonlinear optics. This is another experiment in which we have a plasmonic germanium antennas, and we scan the antenna with a confocal infrared microscope based on Cassegrain objectives. So this is the transmission through the antenna. You can see that where the antenna is located, you see lower transmission of in the confocal map. And then one can excite third harmonic generation with the ultra-fast mid-infrared pulse. And indeed, plasmonics has been used very much in order to boost nonlinear effects at the nanoscale, exactly because of the extreme enhancement and confinement of the local fields. And indeed, if we filter out the third harmonic generation, you can see we have a bright spot at the antenna location. And indeed, here is the experimental demonstrations with the spectra. These are the spectra of 3 different pump pulses, which are tuned to different mid-infrared wavelengths. And these are the corresponding third harmonic spectra at 3 times the energy that shift with the excitation energy as expected. And then we can study this as a function of the antenna geometry. So as we change the antenna geometry by changing the arm length, we start off resonance, then we come into resonance with the plasmonic behavior, and then we go off resonance again. And indeed, you can see the blue line is the third harmonic generation, which peaks at the length of the resonant antenna. And this is reproduced well by simulations as well. So again, this is probably, to the best of our knowledge, the first demonstration of the enhancement of nonlinear effects inside semiconductor plasmonic antennas in the mid-infrared. And the efficiencies, I can tell you, is quite high compared to gold antennas. If we try to do the same experiment with gold antennas, we melt them before getting any photon out of them with the third harmonic generation. And my time is over, so I will skip, and I'm sad to do this, the last slide. I will just tell you that in the mid-infrared, you also have the opportunity to detect the field rather than the intensity by means of electro-optical sampling. And therefore, we are able to study the interaction between an infrared pulse and the antenna by following the interaction in the time domain rather than just by looking at intensity spectra. And this gives the clear signatures of the occurrence of the antenna resonances in the interaction between light and plasmonic oscillations. And with this, I want to acknowledge again all the people that did all the experiments. As I said, I was only very lucky to coordinate all these efforts, and thank all of you for your participation today, and I'm here to answer your questions, hopefully.
Well, thank you, Paolo, for the very interesting talk. As you correctly said, now it's time for question. As always, if you want to ask questions, you can either write your question in chat and I will read it, or you can raise your hand or write voice and I will unmute you and you will be able to ask your question. We already have a first question of Shenqian Zhu from Dresden. Thanks for the talk. What is the result after rapid thermal annealing? Have you fabricated antennas using the materials after laser annealing? If yes, what's the performance?
Okay, so I don't know why I stopped the... Okay, yeah, this is... Then, do you see the presentation again?
Yep.
Okay, so I am... so we fabricated antennas, yes, indeed, after laser annealing. Actually, one of the examples that I show you in the beginning, this bow tie antenna here, is a germanium antenna fabricated with very heavily doped germanium films. This is fabricated by focused ion beam milling rather than electron beam lithography, and was studied with infrared AFM nanoscopy. And indeed, with laser annealed materials, we were able to reach much higher plasma frequencies, and we were able to demonstrate that the antennas could resonate at such higher frequencies. If I'm not wrong, this experiment was done around 5 or 6 micrometer wavelength, so much shorter wavelengths than the one you saw before, and indeed we were able to demonstrate the antenna behavior. Regarding rapid thermal annealing, there were some attempts, but they did not give conclusive results, and they were not published, and actually I'm not really in the position now to give you numbers for those. So I presented the laser annealing because I can tell you that was the most successful one. And if you want the reference for this experiment here, it's in the review. Sorry, I didn't place it here, but it's in the review.
Okay, we have another question from Denis Seletsky. Thank you very much for an excellent talk. It seems that there is a visibility increase damping for the cases with highest doping. Have you quantified the dependence of the gamma, the damping, on the doping concentration?
Yes, we have, and it increases indeed, and it's quantified, but I think that the answer to this question should first stress one point, that if you consider the scattering rate by itself, or if you want, if you consider the imaginary part of epsilon by itself, this does not tell you much about how good your plasmonic performance will be. Because if you have a higher doping and you have a higher plasma frequency, you don't only have higher losses in terms of scattering rates, but you also have, for a given working frequency, you have a lower penetration of the fields in the volume of your plasmonic antenna. So it's true that the volume losses increase, but it's also true that the fields do not penetrate the volume so much anymore. And indeed, if one wants to take a figure of merit for losses, it has been discussed in the literature. There is a nice, there are a couple of nice papers, one by Jakob Kurgin, for example, that discuss that the proper figure of merit should be something such as the ratio between the plasma frequency and the scattering rate. So higher scattering rate, which indeed occur, you're right, and they can be quantified. I don't have the numbers now with me, but they can be quantified, and you can find them in the reference. But they don't destroy the plasmonic behavior so much, because for a given working wavelength, you pay the price of higher losses, but you also take advantage of the higher plasma frequency. And altogether, they balance this effect. So of course, the lower the losses, the better it is, but it's not true that since you have higher losses with increasing plasma frequency, this will be per se detrimental.
Okay, Dennis says, thank you for a very informative answer. We have another question by Minze He. Thank you for the great talk. For the pumping of germanium, do you think it is possible to pump germanium with a continuum wave laser instead of a pulse laser? What would be the difference between the CW laser pumped and the pulsed laser pumped?
Okay, the answer unfortunately is no, and is no by many orders of magnitude. So there is no way that the carrier concentrations required in the mid-infrared can be sustained by CW excitation. You will, it's technologically impossible, and you will destroy your material, even if you could reach those powers. So no, you need pulsed excitation, and of course, this somehow is a thrilling opportunity in terms of devising active devices, ultra-fast active devices, but it has the strong technological limitations that it requires pulsed excitation for sure. The situation is different in the terahertz, of course. So if you exploit semiconductor in the terahertz, then you can find a trade-off where simpler excitation schemes might be used, because you need lower carrier concentrations. And indeed, active plasmonic devices in the terahertz are already established.
We have another question from Rocco Citroni. Good evening to everyone and Paolo. I wanted to ask if the efficiency of the rectenna for energy harvesting application has increased, or is it always less than 1%? And then if there are news of new diodes for mid-IR and optical frequencies. Thanks.
Okay, thank you, Rocco, and hello. I am not aware of any recent claim of rectennas which have higher efficiencies than those reported in a few papers like 5 years ago or so. So I'm not aware of any development in that field. I still believe that those are concepts that have been demonstrated, because the effect was unambiguously demonstrated, but still the efficiencies for optical or infrared photons is still very far away from practical applications. But I might be wrong. I might have missed something in the literature, of course.
Do you have other questions? If not, I can finally ask mine, because I could not find that. So I have a few questions for you again. Thank you for the very interesting talk and for the nice review. Actually, I found about you reading that review in nanophotonics. So first question, what about, I'm quite interested in non-locality. I've been recently studying non-locality in phonon polaritons. We know we have Chirachi and others which are expert in this physics in plasmonics in metals. What about mid-infrared semiconductor plasmonics? Because it would seem a nice perspective to me is that it is possible to structure semiconductors on a much finer scale, which is the reason we are going to phonon polaritons. But in your materials could actually observe large non-local effects by highly doping structures with very tiny features. Okay,
I have no answer, unfortunately, rather than sharing your opinion. This is a very, very interesting possibility for this platform. We have thought about this, discussed a lot, and never tried it in order to experimentally prove it. But this could be indeed an ideal platform to test some of the concepts. And I would add, since we are talking about, let's say, perspective to test theories, that this is also a very nice platform to test all effects that rely on the contribution of plasma oscillations. Also non-linearities, for example, in the visible range, disentangling the contribution of the plasma non-linearity within an experiment performed on gold antennas is always very hard. Here, we might be in the position, for example, to test all these concepts in a much more controlled way. So this is, I think it's an exciting platform for perspective tests of all these theories, yeah.
Thank you.
May I ask a question if there aren't any more?
I have others. Do you have a question, Vincenzo? A question about the experiment in which you pump with the ultra-fast laser and then there is relaxation. What is not clear to me is how does the T1 compares to the T2? How much the relaxation time from the conduction to valence band compares to the intrinsic line width of the plasmon?
Compares to, sorry?
To the intrinsic line width of the plasmon.
Okay. I would say that the time, I don't know if this answers your question, the time scale that we observe, and which is also confirmed by pump probe experiments on the same systems, is the time scales of the thermalization of the electrons within the L valley, and the plasmon excitation does not represent a further channel, but I'm not sure that I'm really entitled to answer the question.
I'll clarify the question. The plasma, if you dope the conduction band, you have plasmons which have a certain line width, because they die for many reasons. When you actually are exciting the electron gas from valence to conduction band, you are adding another loss channel, that is, the electrons are actually falling down.
Okay.
The question is, are they falling down faster or slower than the plasmon would survive in itself?
Yeah, I think that we are not in the position to see this in this experiment, because actually the losses are dominated here largely and basically only by the interband absorption of the whole plasma in the valence band. So we see a big broadening due to that contribution, which masks.
Okay, so no, so you answered me that the largest contribution is that the electrons get reabsorbed.
Yeah. Okay. Yeah. Okay. Yeah. I would say so. Yeah.
Okay. Other questions? No, I have another one. Can you give me a bit more taste for what are the quality factors you can get?
Okay, this is a very good question. So the quality factors are, let's say, roughly speaking, I would say they compare with those of metals, roughly speaking, without going into too much details, but they come from very different behavior. So one, in metals, the quality factors are dominated by radiative damping. Here they are dominated by internal losses. So one is under damped and one is over damped, if you want. None of them has an optimal balance between the two loss channels, and they are very different resonators, but if you look from the far field, they look very similar to each other.
Okay, I exhausted my line of questions. Is there any other question from our public? No.
I have one.
You have one? Please, Vincenzo.
Yeah. No, actually, it's kind of more what you think, if it makes sense or not. I mean, as you're working with semiconductor and your plasma frequency is lower, makes sense to think that applying, for example, a magnetic field will allow you to have to study interesting effect. Okay, so you're ready.
Yeah, it makes a lot of sense. Yeah. It makes a lot of sense, and you can certainly play with this degree of freedom in order to achieve new responses. I would say that this makes more sense with 3-5 alloys, which have an even lower effective mass, which increases the cyclotron frequency.
So we can think some kind of Hall effect with non-antennas and something like that. You could twist, let's say, you could direct the emission with that magnetic field.
At least you could play with the plasma oscillations. I don't know how much.
Yeah.
But of course, you need to have some strong response in the mid-infrared, and for this, you need very low effective masses. So I would go for 3-5 materials.
That's a good and interesting advantage.
Yeah. So this is something we are really considering. So I will be happy to discuss it. In the meanwhile, it's dark here and I didn't turn my light on before, so I'm disappearing slowly.
Well, you're disappearing at the right time.
Okay, yeah, indeed.
There are no further questions, so at this time, I think that with this we can conclude this episode and this second season of MIDI. Let us all thank Professor Biagioni again for this amazing talk, and also all the other great speakers who presented their results during the previous weeks. And of course, we do thank you all for your attention, and I hope you enjoyed the second season as well as we did. Bye, everyone.
Thank you. Bye-bye. Ciao.